Hi, this is a video talking about dissociation and writing dissociation equations, like what an ionic compound does when you add it to water, and then also doing some calculations. So if we start here and we think about, so dissociation is just when you do have an ionic compound that is soluble in water. Remember, they're not all, and we have those solubility rules, but when they are, remember how the water, like if I have a cation, the water is going to surround it and hydrate it, and the negative, partially negative end of the water is going to be attracted to the positive cation. And then, like the anions, it'll be similar, but the water will orient itself so that the hydrogen part of the water is closest to the anion, because the hydrogen end of water is partially positive. So because they're surrounded like that, the ions are truly separated. So if I were to put them in a beaker, I'm going to have just those sodium ions, just those chloride ions in water. So the way that I can write that as an equation is to write and show that the solid, when I add it to water, and I'm going to put AQ here to show that, then I'm going to get those ions, and I'm going to put AQ just to show that that is only if they're in water. And there's one of each because of the formula being in a 1-to-1 ratio. Aluminum chloride could be similar, so aluminum will break up and get surrounded by the water. But this time, you're going to have not just one, but 3 of those chlorides. And we're going to put the 3 in front because they're actually literally 3 of them, and they're not together anymore. And then this would be that aluminum plus 3. So, a couple questions. Here's one of them. I'm going to move myself. What happens if you then have, now we're going to introduce molarity into this. So, if I have that sodium chloride, remember, we're going to put the little ions in here in a 1-to-1 ratio, and these are only if it's aqueous. If this is 1 molar, if I make a 1 molar solution of this sodium chloride, I'm going to grab a mole of sodium chloride, which is 58.44, I think, for the molar mass. There'd be that many grams, and then I would put that into a liter of water, or add enough water till I get to a total of 1 liter. But anyways, once I add it to water, this no longer exists. And I'm going to look at my mole-mole ratio, though. For every one of these, 1 mole of sodium chloride, I get 1 mole of sodium ions. So because they're in a 1-to-1 ratio, that would mean then that my molarity of just the sodium ion is 1.0. So I have 1 mole of sodium ions per liter of that solution over here. And again, this one's in a 1-to-1 ratio with the sodium chloride. So this would also be the chloride, there'd be 1 mole of chloride ions per liter of solution. So the original solid is gone, and then your ions, depending on the mole-mole ratio, the concentration of them will change based on that. So let me just show you some more examples of that, because that can be kind of weird. So here's another example. So anytime I'm talking about a compound, I give you the molarity, and I want to know anything else about the molarity of the ions, the first thing you want to do is write that dissociation equation. So you want to break it down. And again, you can visualize it in a beaker. So I would have that cobalt-2 all by himself with water around it, which I'm not going to show. And then the other thing, this one's a little different. I have a polyatomic ion, nitrate. The nitrate is going to act as 1. So there's going to be 1 nitrate, and then there'll be another one. So they're going to stay together to that extent. So I'm going to put a 2 in front to show that for every 1 cobalt plus 2, I have 2 nitrates. And again, these are aqueous. So if this is 0.5 molar, I have a half a mole of cobalt-2 nitrate in per liter of that solution. Then because these are in a 1-to-1 mole ratio, and you could even, if you wanted to show it, like 1 you're going to have 1 cobalt for every 1 cobalt nitrate. You're going to then end up with 0.5 molarity of cobalt ions, so 0.5 moles of cobalt plus 2 in that solution. Whereas if you're figuring out your nitrate, again, you're starting, if you want to actually show the work, if you're more visual, so you have that 0.5 molar of the cobalt nitrate that you made, but then you're going to have a mole-mole ratio of 2 nitrates for every 1 cobalt nitrate. So this would be double then. So this would be 1.0 molar. So in the solution, there's 1 mole of nitrate ions per liter. And then also, sometimes I'll ask you the total, like what is the total molarity of the ions in the solution then? The total molarity would be 1.5. We'd have 1.5 moles of total of ions per liter of that solution. One more, again, we can kind of visualize. So this is iron 3 chloride, and it's a solid, but if I tell you go make a 1 molar, you're going to figure out what the molar mass of that is, add that, and then add enough water till you get to 1 liter. So I would have the iron plus 3, aqueous, at that. Remember, it's completely separate than the chloride, and that's aqueous. And then remember, I'm going to have 3 of them because of the formula, but they're all by themselves. That's why we put the 3 in front. So then this is another one where, so if I have I made a 1 molar solution, then because these are in a 1-to-1 ratio, I'm going to have, after everything dissolves, 1 molar of iron plus 3 ions, so 1 mole of iron plus 3 per liter, and then 3 times that, or 3 molar for the chloride, or a total of 4 moles per liter of ions in this solution. One other type of problem here is, we can draw our beaker if we want. We don't have to, but so here we have aluminum chloride solution. So again, anytime that we're talking about ions, you're going to want to write that dissociation equation. So aluminum ions, and then you're going to have those 3 chlorides. This is similar to that one we just did with the iron. And again, if you wanted to visualize it, that's what we have. So in this problem, we have 73 milliliters of the solution, and we know that it's 1.5 molar. So what we're going to want to do is think about, we know that molarity is moles per liter, and this is 1.5 molarity of the aluminum chloride, the compound. So what I'm going to do is I'm going to solve for the moles of aluminum chloride first, and then per liter, I need to convert this to liter, move the decimal 3 places to the left. So when I solve, I'm going to have my moles of this is the whole compound, the aluminum chloride. I'm going to get, what do I get? I have it on my paper. I'm going to round it to 0.11 moles of aluminum chloride. Now I'm ready to go up to the equation and do my kind of reasoning with the coefficients in the ratio of the moles of using those coefficients. So if this is 0.11 moles, it's no different than if that were the molarity now. When that breaks up, I have a 1-to-1 mole ratio. Again, if you want to think about it, you have 1 mole of aluminum per 1 mole aluminum chloride. That's how we know this is going to be 0.11 moles of aluminum ions. And then similarly, we would have 3 times as many, or 0.33 moles of chloride ions. So the question though is asking how many moles of chloride. So that is my answer. I didn't need to do the aluminum, but it didn't hurt. So I hope that helps. And then you guys are going to have some practice. So if you have any troubles, just let me know.